Michael Bousfield is technical director at Cascadia Windows and Doors. He's one of North America's most experienced technologists in fiberglass window and door technology. Involved in developing the world's first Passive House certified fiberglass window, as well as the world's first fiberglass window wall, Michael works closely with Cascadia's commercial clients, creating custom solutions for high-performance fenestration systems. He also values opportunities to discover and exchange knowledge. This includes staff training, leading research and development projects, and public speaking and education on behalf of Cascadia to the industry. So with that, Michael, please take it away.
Thank you very much, Zach, and thank you for everyone for tuning in on today's session. Today's session is a topic that's relatively new to me and to us at Cascadia Windows in terms of technical learning, testing, and research. And so two things from that. Number one, because we're quite new to it, I want to stay humble enough to admit that we have done some testing, we have learned some stuff that's valuable, and we've selected what we think is valuable for you to know, and we want to share it. And that's going to be over the next 30 or 40 minutes. But also, we're inspired to do more testing, learn more, and get feedback from you all as to, like, what do you want to know more about? Or like, what more do you need to know in order to add information about wildfire and wildfire's effects on fenestration to make your choice, your selection process and choices more effective in design and in engineering. So today's session will kind of go like a story of what's happened over the course of most of this year for Cascadia learning about testing and doing research on wildfire's effects on windows. More specifically, I'm first going to introduce our company, if for no other reason than it helps everybody have a better bias filter. And I'm going to spend a couple of minutes at the beginning of the technical portion of this describing why fiberglass as a window frame material. If you've listened to us present before, this is going to be a very abridged version. It's a few material characteristics that I think is going to be useful as context for later in the session. And the rest of the session, we'll look at wildfires, big scale, and then buildings, and then windows, because windows happen to be a specific vulnerability in buildings when we're thinking about resistance to wildfire. And of course, I'm going to show you all the gory details from some early testing where we burnt down some windows and think we've learned some stuff. So Cascadia. Cascadia is a manufacturer in the Pacific Northwest of fiberglass framed windows and doors and a thermally improved cladding support system. Those windows and doors include a fiberglass window and system, complete with doors, and a fiberglass window wall, which can be Passive House certified at a buyer's option. They end up best fitted to large-scale institutional projects and multifamily buildings, higher-end residential or custom residential projects, and when it relates to walls, this is an example of our fiberglass thermal spacer on a commercial project. So the common thread through all of that is that we specialize in fiberglass as a base material for building envelope products because it helps, well, amongst other things, combine durability and enhance energy performance of building envelope assemblies, which is a great segue into why fiberglass? And this is going to be more look at materiality and material science in just a minute or two. Starting from a bigger picture, narrowing into the material science, Cascadia as a manufacturer with fiberglass is a little bit of an outlier. So we're not representing the entire scope of fiberglass window industry here, but rather a portion of it. Fiberglass windows, when our team first got introduced to them and started to build out a team of business owners and technologists, we looked at the window industry in general and we understood that commercial grade for window products and energy efficient for window products used to be mutually exclusive terms. And with the exception of Cascadia, who specializes in commercial grade windows and doors, actually this exclusive terms comment, it still stands today for the most part. Most fiberglass window manufacturers make products that are more durable, but they're more durable versions of like relatively similar PVC products. Those fiberglass products are not necessarily commercial grade in the sense of the size capabilities or the resistance to exposure that you'd expect from a commercial product. So we're speaking from a little bit of a niche application here, but the material science is just science. To make fiberglass, fiberglass is made from long strands of glass fiber combined with a thermoset resin. To use another construction material as an analogy here, you might think of reinforced concrete, where the strands of glass represent the steel reinforcing in concrete, and the resin is the concrete that holds it all together and provides a finish and maintains the shape. When fiberglass is manufactured, long strands of glass fibers get oriented into the necessary shape for the tooling to produce the end profile. Then those fibers get coated with resin, and the resin is not always green as it shows in this photograph, but you can make it that way if you want. The material gets pulled through a die that heats the material and gives it its shape. And finally, you have a unlimited length, two-dimensional profile that you can cut and then manufacture into anything you want. Of course, in our case, we're speaking about window frames most of the time. And when you look at the end product that you can get when you take that material and you fabricate it into a window frame, it ends up giving several strength characteristics that are favorable for making commercial windows. So about 10 times stiffer than vinyl from a structural perspective. The fact that it's a thermoset resin, and more specifically for you chemistry buffs amongst us, it's a polyester. Interestingly, that is different than a different form of polymer than a PVC or a vinyl polymer, which would be a thermoplastic. The biggest difference between those two families of polymers is that a thermoset cannot melt or deform with heat. So we'll just pin that in our mind for a few minutes to come. Because of its enhanced resistance and stability to high heat or to extreme cold, in fact, it can, as a finished product, it can withstand extreme temperatures without deleterious effects. And it ends up with a much longer model lifespan than most other materials from those fundamental properties. And so if you start to think about it, okay, to round out the question, why fiberglass in the finished product form as window products? There's a lot of strengths and weaknesses that materials have. And when you are, as a designer or an engineer, you're thinking about material selection or product selection based upon the principal material in a window product, you're trying to optimize for something. You're trying to optimize, in the case you might consider aluminum, you'd be optimizing for strength and longevity. If you're trying to optimize for thermal performance, your mind might go right away to PVC. If you're trying to optimize sort of more comprehensively, you don't want any sort of lower points, or you're looking for the lowest carbon impact, you might be looking for fiberglass. But I want to introduce a fifth potential selection criteria that we all might have in this case, and that is wildfire resistance. And if that were particularly interesting to you, you'd be prioritizing metal or fiberglass, as it turns out. So with that in mind, let's look at wildfire, and we'll start a little bit big picture here, but we'll get to focusing on windows in just a moment. So looking at wildfires, I'm not going to spend much time convincing everybody that wildfires as a problem are a big problem. They're a problem that's persistent, and it is unfortunately a growing problem. I don't need to spend 30 minutes of this presentation presenting evidence to that effect. But a little bit closer to home, do you personally know someone who's lost a building in a wildfire? I hope it's not you personally, but we have a big crowd on this presentation, so maybe some people have. Most people do at least know somebody personally who has lost a wildfire. At Cascadia Windows here, we all do. And in fact, I'll tell you a little story about a building that is well fitted to this part of the presentation. This little building, this little home in this picture was a panabode, so a solid log home that was a manufactured log home. that eventually became or was bought by our president. So why? Our president was looking for a building to put on a recreational property he had purchased in the province of British Columbia. And he just had a tiny little fishing cabin on that. He wanted to improve it to be a recreational, a big cabin for his family to come and enjoy the lake. And he found that through an acquaintance, there was a property owner in Greater Vancouver, British Columbia, who had a agricultural property, and this building was a second home on that agricultural property, and they didn't need it anymore. They weren't using it. It was about 60 or 70 years old at the time, and our president was able to purchase it relatively cheap with the intent to disassemble it, move it, reassemble it, and put it to a new use, which is a pretty cool idea. And he did it. He disassembled it after individually labeling all the components and took it apart like a Lego kit. It's not sealed together. You can literally lift it apart if you just take out some key fasteners. So he built himself a map, labeled the materials, loaded them up, took them 4-hour drive outside of the city, brought them across the lake to the recreational property. Before assembling the cabin, built a modern wood frame floor assembly, complete with a few reinforced concrete footings to receive the cabin, and then began to assemble the cabin. And he did. It worked out quite well. He didn't need fiberglass windows in it at this point in time. He was able to reuse the existing windows because it was just a seasonal cabin. And so he and his family enjoyed this building for about 10 years or more. But everybody knows where I'm going with this conversation. And it turns out that this location was at Loon Lake, British Columbia, which was the site of one of the most intense wildfires that we've seen in recent years. And about 5 years ago, 5 or 6 years ago, this cabin was lost to that wildfire, along with several dozen of the other cabins that were on that water access only side of the lake. And that fireball in that haunting photograph is actually our president's cabin. So we all know somebody, and this topic is near and dear to us. But it's interesting to note that we think about, and at least I thought about this topic in terms of that cabin, which was a wood cabin in the middle of the forest. But that's not where the majority of our building stock that is at risk of damage from wildfire is located. About 1 in 6 Americans live in an area with wildfire risk. So that's obviously far more buildings than the odd recreational cabin in the woods. So let's look at wildfire resistance of buildings more generally, because it is a more widespread risk. We can see, in fact, from all over the globe, that attention on this topic is intense and growing, but not matured yet. But thankfully, we can take examples like this architect in Australia who had enough of seeing communities destroyed by wildfires and decided that from that point forward, all of his buildings, just as a basic aspect of the construction and the design, are going to include wildfire-resistant exteriors. It's not building code in his area or most areas yet, but it's important enough that not only early adopters and concerned architects are getting on board with both learning and implementing this knowledge, but it's insurance companies as well who are doing hard math and are starting to change the insurance premiums in some areas. And it will be logical that insurance companies, as building methods and building products become more mature and more available, insurance companies will no doubt further alter their premiums and discounts in response to the wildfire resistant character of the buildings they are insuring. Coming to, how do we see communities educating their occupants, their builders, their designers for resistance to wildfire? Well, actually, this little extract comes from a small community in British Columbia. But I liked it when I pulled it off their website because it taught me a few things. And it first showed that this concept is not just about selecting building materials that resist fire. That obviously will be a part of it. But the strategy of wildfire resistance is more holistic. It's the whole property. And if that property is beyond the edges of your buildings, then it might have trees on it. So it starts as far away as the trees that are on your property away from your building. I didn't know until I did this research earlier this year that coniferous trees are highly flammable, but deciduous leafy trees are less flammable. So that's interesting. Some property owners have some control over what type of trees are nearest to their buildings. So this could be useful information. And then closer to your building, plants, leaf, twig, surface fuel. That's more user behavior and user controllable, but it's an important strategy to continuously maintain to enhance wildfire resistance of buildings. And when we're talking about surface fuels, it even comes to that wood fence that comes from the back of your property and connects to and touches your house, where the fence meets the middle of your house. So think about that fence material as well when you're designing things that will be permanently on and around your property next to your building. And then thirdly, your building. The building materials themselves, through your selections as a designer or an engineer or a builder, will have either a better or worse effect on enhancing resistance to wildfires, of course. And this has become useful guidance as we see, California, for example, rebounding from the devastating wildfires that caused the loss of many homes. And it's interesting to see out of that attention and out of that effort that studies are being done and recommendations made to include Passive House as an excellent and well-fitted design guideline for as much of that rebuilding as people are willing to adopt. So wildfire resistance and Passive House therefore coexist quite happily. They're not dependent on one another, but they definitely coexist, and we can make buildings better by implementing both. Which brings us to windows, because they're both important in Passive House designs and they're important in enhancing wildfire resistance. Why about wildfire resistance? Well, it's because they're a vulnerability. So thinking about those three aspects of the best practice for enhancing a building's wildfire resistance, starting outside the building, which is intentionality about landscaping. That's that furthest out surrounding environment piece. And then the second piece, controlling the accumulation and, unfortunately, sort of depending upon the occupant control of surface fuels. That's user behavior. That's closer to and up to the outside of your building. And then building materials, building selections during design. So those, out of those three approaches, that last one, the building materials selections during design, that 1 out of 3 is a much more reliable place to aim our attention in like a learning session like this one, because at a population level, we're not dependent on site specifics. We're not dependent on user or owner behavior as much. Now, windows are part of that last most important piece, building materials. So they deserve specific focus because a window is a specific vulnerability. And what do I mean by that? Well, if you had a massive wall of fire pushing through a forest and it totally engulfs your building, then your building is unfortunately toast regardless of if it had a window or not. And therefore, we're not talking about poor Cascadia president's cabin in the woods that got completely destroyed by a massive wildfire. But instead, we're talking about the large proportion of buildings that are next to a wildfire, and that wildfire passes by, and that wildfire can give off heat, embers, or small chunks of burning material that fly through the air and land because they touch a building. And if it landed next to the base of a wall, it might make the exterior of that wall suffer a bit or become damaged, but the building wouldn't burn down. But if it landed at the base of a window, it might break the glass, set the frame on fire. It could cause the building to be lost from the inside out. And therefore, that's why we say windows are a specific vulnerability, because they could cause the loss of a building where if there was not a window, there was a wall, the building would have survived. And that's what happened to the building in this photo. You can see that the outside of this wall, left and right of the window, it has not been subjected to a massive inferno of a wildfire completely engulfing the building, yet the building was still lost. And it's quite easy to project that that could be because the windows at some location around the building allowed fire to penetrate, and then the interior things such as the curtains, the interior trim around the windows, even the furniture caught fire after the fire penetrated through a window. So windows are a key weakness, yes. Now, there's limited industry knowledge about them compared to some other materials like wall and mineral wool insulation and non-combustible roofing materials. So because there's less, not zero, but less knowledge about windows specifically, there's less guidance about it. There's less best practice guides, regulations, but there are some. At a product level as well, there's very few options. Some exist in the United States. None are made in Canada until recently. But again, there's more than zero. So let's look at how window products themselves or the selection of them can rely on testing or published guidance, like from anywhere. It doesn't have to be Canadian or Californian. It doesn't matter where the author was living when they created a test standard. But in fact, there is a test standard published in California and referenced in some regions by their codes. But that standard is now being relied upon outside of the borders of California, and happily, it is becoming useful in other locations around the United States and even in Canada. It's referenced in some Canadian guidelines. So we do have a published standard. The standard does include testing and how to test a window for wildfire resistance. So of course, that's interesting. But let's look at, before we dive into that test and what does it look like and what are the results, let's look at where we see it being referenced. And I think it's interesting mostly to see where it's being referenced outside of the California region, where it's sort of connected with requirements to codes and regional requirements. So outside of that geography, even the National Resources Canada has created a guide for wildland-to-urban interface fires for the whole country. And in it, they indicate that windows should be tested to the California test standard for exterior windows. Why a California standard? It's the only published one right now. So it's way better to reference a published standard than just talk more generally. Where else do we see references to or specific requirements for windows and doors in published guidelines? Well, FireSmart Canada, a national organization, created a builder's checklist. And in that checklist, they talk about windows and doors, not at length, but it's in there. And the most prescriptive element of it says, and I'm going to paraphrase here, windows and doors frames should be metal or fiberglass. Like, pretty blunt there. And one of the things that struck me about that is that it quite obviously omits wood, but also PVC. So why would that be? Well, I'll show you some stuff in a minute. Finally, one more. Where do we see from that same organization and others throughout Canada? So outside of the geographic region in California where this that test is created for, wildfire resistance best practice checklist, even in another country, still references that California-based test. So it's not bad. There's a test. It's useful. It's useful enough that it's not geography dependent. So what about that test? Well, Cascadia engaged with a study that was being done by engineers, building envelope engineers, and some fire specialists to submit some windows to be subjected to that test. So what's the test? Well, the test is putting a window in a non-combustible test buck. So essentially build a framed wall, in this case, a steel framed wall, put gypsum on the wall, put your window in that non-combustible buck, and put a big burner of fire right below the sill of the window, and turn it on full blast for 8 minutes. It's like, so what does that simulate? Why 8 minutes? So I don't specifically know, but the fire specialist who was with me as we began doing this testing said that if you have a nearby wildfire, you could have a situation where a chunk of burning material, so basically a chunk of a tree that's on fire, breaks off, and because of the prevailing winds, the movement of all the hot air, just blows over to your building, lands at the base of your building. And if that's a window, now you have a source of burning fuel right at the base of your window. But it burns intensely, and it burns pretty quick. Usually 2 to 4 minutes, it's burnt up and it's out. So we need to study the short-term but intense effects of a nearby fire. And I think the 8 minute was just take the upper end of that 2 to 4 minutes and double it. So if anybody on the call knows more, knows the author of that test standard and knows more exactly why that 8 minutes is part of it, let me know. But the punchline, what must not happen during this test? Okay, if you're on the inside of the window, fire must not penetrate all the way through in a way so no smoke, no fire in a way that would risk setting something on fire, like the furniture, the interior window coverings, or the wood trim. So this does not mean that after the fire test, the window is as good as new. Wipe it off and carry on. No, the window is going to get destroyed, more or less. But the window's job is to take that damage and protect the building behind it. So here are some photos from our setup and from the testing itself, and I'm going to describe what happened as Cascadia's observed the testing in progress. This is preparing the opening before putting in the window. Putting in the window, when you turn on the fire, the glass is going to break for sure. For sure. Doesn't matter if it's tempered, thick, thin, it's going to break. It's going to break at different time periods, depending on what glass it is. But the outer pane of glass, and that's critical, the outer pane of glass is going to break for sure. You just got to make sure the inner pane doesn't. Okay, so what did we learn? Well, more specifically, what did we submit for the purpose of learning? So we submitted 4 different levels of window. Let's I don't have a word for this. Let's call this anticipated fire resistance. So we designed slight modifications to the same fixed window where we kind of divided our modifications into 4 levels. To get inspiration as to how to pick those 4 levels, we looked at the code in California that references the published standard for the testing. We noticed that the code doesn't only use that testing as a path for compliance. But in addition to that path, there's also a prescriptive path that says, like do this and this and this, like a little recipe, include some tempered glass. And so we wanted to build our first level of product, which would be below, therefore not worse than or non-compliant with the prescriptive standard. Essentially, we're building one window to go and fail. And then the second level of window we built, which would just be barely in compliance with the prescriptive level of that part of the code, but not better. So just barely meeting the prescriptive standard, and then we're going to test it and see if that truly is good enough, if it truly passes. Then we threw everything we could at the third level. We had fire-resistant resin in the resin of the fiberglass itself. We put rock wool into the ends of the frames, not all the way through them, but rock wool into all the holes. We did fireproof sealant as a heel bead. So we really improved the window the best we could within the realm of economical things that a buyer could order a product from us and still select those things. They're just not packaged up as available options, but they could be. And then the final one was, let's go to a laboratory that builds glass for chemistry work and get some fireproof glass, and let's pop that in there so that we can isolate the damage and observations to just the frame. Then we tested these, and they all worked, even the most basic one, which really surprised us. But more specifically, we learned separate things about glass, and we learned about the frames, and in this case, fiberglass specifically. So what did we learn about glass? Well, just to recap, we learned that fiberglass it was surprisingly good for our expectations. All those 4 levels worked. I want to quantify these observations from this point forward. Unless I say otherwise, I am talking about observations taken from a test sample quantity of 1. So for you physics nuts out there, n equals 1, right? This is one test for each increment that we made observations about, which is indicative and teaches us a heck of a lot, but it's not repeated 10 times and or even a few times, and then taking like sort of the minimum and the maximum, reporting that. That doesn't exist yet. So what did we learn about glass? Well, actually, we saw this throughout all of the testing. And this has nothing to do with a fiberglass frame. This is just good information for everyone. 6 millimeter glass or quarter-inch thick glass, which is on the relatively thick side for residential windows, that's a good idea. Thicker glass is a good idea, like across the board. What else did we learn about glass? Not tempering the exterior light is fine. It might even be a good idea. And when I say it might even be a good idea, I was previously like recommending this pretty hard, as in like this will actually help more. I watched some test results presented from Underwriters Laboratory that suggest that the outer light could be tempered, and statistically it's not going to be much worse than if it's annealed. But here's my thinking when I first wrote this. On the right-hand side of this slide, you see a picture where 2 layers of tempered glass in this double glazed IGU have been subjected to a test, and the test has passed. But the outer pane of glass cracked as we expected it would crack, and it cracked about halfway through the test. So it's quarter-inch thick tempered glass, both of them are. First one cracked. When tempered glass breaks, it shatters violently. And often a chunk falls out, as you can see in the bottom right corner of this window. Do you think if we repeated this test with this glass 10 times, that all 10 times that piece or smaller would fall out only? Or do you think that there's some instance in that period of 10 times where most of the glass happens to fall out? Because it's a very random break pattern. So we think that if a larger piece of this outer pane of glass happened to fall out, then it would more fully expose the inner pane of glass to the fire that was, continuing on, and it would increase the risk of failure to the inside of the glass. By comparison, if the outside glass is annealed, it will crack, and it will crack sooner than if it's tempered, but it tends to stay in place. Like a cracked annealed glass, if it's captured on all 4 sides by window frame, still tends to stay there. So it kind of stays there like a shield hanging in front of the inner pane. And you only really care that the inner pane survives. Now, about the inner pane surviving, temper the inner pane. For sure, that's probably the most significant glass observation. Temper the inner light. And so this is more photos from the back side of that same photo I showed on the right-hand side. So the inner pane of glass that is tempered did survive. The outer pane that was tempered in this case cracked about halfway through the test. About 20% of it fell out. The 80% of it stayed in place during the test. But we worried, just like making observations as the 8 minutes dragged on, that if this was, 20% of the glass left and 80% of it fell out, would the inner pane have survived? Maybe. But if the test went 10 minutes instead of 8 minutes, would it still survive? I don't know. Maybe not. That's why we think there's a variable there, and we're recommending anneal glass unless you need to temper it for other purposes like safety glass on the door. What did we learn about frames? We learned that heavy multi-chambered fiberglass frames kind of help themselves. So even the fiberglass without any fire retardant passed and fared quite well. And so I've got some cutaway where after we did the test, we used a saw to chop through the fiberglass frame. So I'll show you those photos. This is before the test. So as you can see, before the test, we have these multiple chambers. They're normally foam filled, but we put about 2 inches worth of mineral wool just in the more robust version of these in the test. But most specifically, look at the fact that there's multiple chambers. There's not just one big open cavity. Even the glazing leg that's in front of the glass has 2 walls of material and an open cavity in between. Okay, so like what happens when you burn that down? Well, we burnt it, and then as you can see in the sample here, it looks like all these hairs are sticking out of the surface of the burnt frame, but that's because we took hand tools and we roughed it up so that we could see the the glass. These are actually strands of glass that were in the profile. If before we roughed it up, it doesn't naturally do that. So you can see the rest of the frame is just as it is. But in this location, we observed that the outer surface of resin on fiberglass is combustible, so it catches fire, it burns away, but it burns away that surface of resin that's on the outside that in the natural product, it's there to, accept paint. And then what's revealed underneath is a layer of glass that cannot burn, and it acts almost like a fire blanket locally to what's behind it. Heat transfers through, but not fire. So enough heat transferred through that it melted the foam insulation that was in these cavities. But you can kind of tell that the heat didn't penetrate too far into this multi-chambered frame. Like the second chamber got hot enough to make the foam recede a bit, but not melt. And then inboard of that, it's totally fine. Like I remember walking around, I'm going to go one slide back, few slides back. I remember walking around in the test hut here, like at the 7-minute mark where the fire had been screaming away for 7 minutes, and putting my hand on the window frame. And the window frame's totally fine. It's a little bit warm, like obviously, but it's not hot to the touch. It's properly warm. So we learned that the portion of the frame, the inner half of the frame that's connected to the glass and it's connected to the wall, the building, that is protected by the fact that the frames are sort of deep, they're multi-chambered. We actually wanted to see what would happen to the frames if we subjected it for longer than the 8-minute test. So for the sample where we had the fireproof glass as the IGU, we did the 8-minute test. We took a 5-minute observation period to make sure it was out and just to take some photos. And then we turned the test back on for over 20 minutes. And we kind of just sat there getting bored because as it turns out, it takes about 8 or 9 minutes for the outer resin to combust. And then once it's combusted and you've got kind of just dirty glass on the outer surface, not much happens after that. I guess eventually something would, but 20 minutes later, the frame was pretty much exactly the same visually and when we cut it as it was after just the 8-minute test. So we learned that not all other windows are going to react the same way. So we also, or when I say we in this case, the engineers who invited us to participate in this little study, they also bought some vinyl products, some basic vinyl products just off the shelf of a building supply store. So these are purchased retail. I'm not going to tell you who's the manufacturer because they didn't have a chance to participate in the testing or comment or anything. And we were not trying to play Mythbusters. We weren't trying to prove or disprove anything that was claimed. No, we just wanted to see what is the result of doing the same test on products that are manufactured in North America and widely used, commonly available in North America. We made some observations. Thinner glass, like 1/8 glass, 1/8 inch, breaks easier than thicker glass. We also noticed, and this was important, vinyl frames both burnt and distorted with the heat of the fire. Whereas the heavy fiberglass frames, they burnt on the exposed surface, like I showed you, but they didn't distort because fiberglass doesn't melt or deform with heat. Thermoplastics do. And we observed that frame distortion increases the likelihood of a fire breach. Because if you have a sash and you have a frame, and then they distort, they open up a gap between them where the fire can penetrate. And when you think about the material characteristics of those two samples, when you're thinking about vinyl, there is a glass transition point with all vinyl materials, and the material hasn't melted yet, but that is the point where it becomes soft and rubbery. It's about 180 degrees Fahrenheit when that happens. It melts at and like fire breach can occur in this situation because it becomes soft and rubbery and it doesn't support load the same way it does at the normal surface temperatures. It melts at a much higher temperature and it ignites even beyond that. So 736 degrees Fahrenheit was a sort of an average that Google search returned to me. Fiberglass it doesn't have, so it's quite different at the practical levels here. It doesn't have a glass transition point. It will never become soft and rubbery. It cannot melt. It'll burn slightly higher temperature than vinyl, but it will ignite and it will burn just like vinyl. And full disclosure, the temperatures experienced during this testing for the outside surface of the windows way beyond these ignition temperatures. So this is not a test of whether or not the frames will ignite. The frames will ignite for sure. An aluminum window will melt the thermal break and then set it on fire. A wood window will set on fire. It's like this test will set your window on fire. But overall, how the frames fare during the test, that's going to differ based on the frame material. So this is the vinyl frame before and after. As a couple of closing comments here before we dive into questions, I am pleased to describe to you a very limited amount of some interesting research that I saw early days for some manufacturers engaging with that same research team to bring more to the community. They were trialing some temporary window covering materials, both on fiberglass windows and PVC windows. They were trialing the materials, trying to identify what might be the base material for a product that could be offered to existing owners of windows who are not ready to do window replacements or window retrofits yet, if they could have an affordable product to keep in their basement, and if they're going to get evacuated, hang or bolt these products temporarily in front of their windows to increase the likelihood of survivability of windows that are not likely to survive otherwise. And those materials, and this is after the test where the material is like bunched down below the window, they fared quite well. So it is my hope that those companies take those early successes in this testing and materialize some products at the consumer level. Early testing looks quite good with that. We tested vinyl and fiberglass windows with these approaches. For the fiberglass window, with a sort of a consumer level product covering the window after the test, the window was perfect. You could have wiped it off and continued using that window. The interior seals of the IGU between the glass and the spacer bar didn't rupture. The paint was okay. It was quite impressive. Yeah, we also tested it with vinyl. These two samples on the right are what happened to the vinyl windows with the window coverings. So they melted, glass broke, the windows are destroyed, but they passed the test in the sense the building wasn't lost. They kept the fire out of the building. So that early research is going to be, I hope, valuable for existing building owners. But you can kind of see the difference in the fiberglass versus the vinyl. I mean, they both passed the test with those protective coverings, but still you could notice the difference. So the key takeaways that we took from this is that, yeah, that we as a design community can identify 3 layers of controls where us as designers and the owners of buildings can enhance fire resistance. So surrounding environment, like close but beyond your building, is one area. Surface combustibles, including stuff right next to your building, that's the second area. And building materials is the third area. You have at least partial control of these, almost always. With that last one, which is most important during design, because you're making decisions that last a long time, target weak points. I mean, this is not a new concept introduced just related to fire resistance. Targeting weak points is something that Passive House is built on. But for windows and related to fire, choose heavy fiberglass or metal for your frame system based upon what we have seen so far in testing. And related to glass, choose relatively heavy glass thicknesses, such as 1/4 inch or 6 millimeter, and above all, temper that interior glass light. So for full transparency here, the example product used in the photographs and referred to in this learning session when it was the fiberglass window, that was a product line called the Universal Series, manufactured by our company, Cascadia. And lastly, before we open up to questions, what did Cascadia do about these learnings? Well, number one, we identified more testing and are investing in it, and that will be occurring in the next couple of months. But we also did something for specifiers who might be interested in just reacting right now based on the information now known. And to sort of help those amongst you, we developed 2 variants to our product line where without any enhancements, our regular universal series, it was referred to as just our normal product, but we can enhance it to the point where it will pass that test with certainty. This is just a few minor enhancements, including that the glass package meets the minimum that we saw successful. The estimating team charges a few percent, 2, 3, 4% for that wildfire resistant standard option. It's a good wildfire resistant option, and you don't have to be just building a cabin in the woods to make use of this. You can have this on any building. And then for those of you who are building your own cabin in the woods and you want something a little bit more enhanced, also passes the same test. So quantifiably, I can't tell you much about a difference if you want my answer to contain numbers, but what the main difference that it does have is it's built with a fire-resistant resin in the fiberglass frame. So longer time to ignition, shorter time to self-extinguishing, less flame spread, but they both pass the test. And that second option would cost a buyer about 8 to 10% more than the baseline. So that's what Cascadia did with this information, sort of like in the same year that we learned it. That's it. I now value your questions, and I know that there's a number of them in the chat. So Zach and team, please curate as you wish.
Yeah, absolutely. Well, Michael, fantastic presentation. Thank you very much. And yeah, there's lots of really thoughtful questions and comments in the chat. People who I know have been impacted themselves by wildfire and who are thinking very thoroughly about how to respond and create more resilience in buildings. So I think we're in for a really great discussion coming up here. So let's start with Stefan. I hope I got close to pronouncing your name correctly. I know you had 2 questions. Maybe we could start with one and then follow up with a second one later in the queue. So Stefan, if you're able to unmute yourself, that'd be great.
Good morning.
Or if not,
yes,
yeah, great.
It did take a little moment. Thank you very much.
Yeah, no worries. No worries.
Yes, thank you for the presentation. Quick question. What would be the difference between the Californian standard and European standard when it comes to fire resistance? That's the Californian standard as the only one in that context.
That's a great question. The short answer, unfortunately, is I don't know. And because I don't have a good answer for that question, I love your question. It's going to inspire some more research and learning for Cascadia. I can tell you why Cascadia selected the California standard to follow, even though we're a Canadian company, is because not only do we sell products to the California market and in fact the entire United States market, we also sell products to Canada, the whole Canadian market, and in Canada, there's been adoption of and reference to the California standard, whereas the European standard is useful and interesting, but we at our early stage right now haven't used it as the basis for the initial learnings because it's not referenced in the best practice guides where we can point to and say, hey, our own domestic regulators are not yet making this code, but they are publishing recommendations that indicate to follow the California standard. So anyway, thank you for that question, for bringing that out. The short answer again is I don't know what the specific differences are.
Great, thanks, Michael. And we'll get back to you, Stefan, for the follow-up about the standard if you like. So Alice, you had a question.
You'd spent a lot of time comparing the fiberglass to the vinyl. I was just curious how metal clad windows, and then right at the very end, you included that on one of your slides. But the aluminum clad wood windows, are they good for passive as well as wildfire?
Good question. So related to windows that can meet the passive house standard before we look at the wildfire piece, yes, actually all 4 major frame materials, wood, vinyl, aluminum, and fiberglass all are well represented within passive house certified products. From a combining materials perspective, some of those require clever designs of the intermediate materials to enhance performance, but they all exist. So you could use them all in a passive house. Now, which ones will likely deliver fire resistance? So any manufacturer could test a product, and if they achieve results, then they could happily claim, hey, we've achieved these results. What we observed is that window frames that are principally based on vinyl have low likelihood, especially North American produced vinyl, have a low likelihood of achieving the results. Fiberglass, maybe. Heavy fiberglass, yes, for sure, obviously. Aluminum, probably yes. And wood windows, I would say that aluminum-clad wood windows will help those windows far more than just wood on the exposed surface. And in fact, if you look at the extract from the Canadian best practice guide, which admittedly does in a separate publication, reference the California test. But before it gets there, there's some recipe-like generalized recommendations. And they say, when I said, I'm summarizing, and I said the windows frames should be metal or fiberglass, there was some nuance there. And I'll scroll I don't have the slides on my screen anymore, but the recording has them. And they said, yeah, metal clad wood or steel or thermally broken aluminum. And so like all of those should be reasonably expected to perform. If you wanted to use metal clad wood, you could have the reasonable expectation that it would perform. I mean, it would be great for you to select ones that actually have testing results that show that they perform. But if you had to make a choice without testing results, yeah, you'd be on the good side of that bet if you had metal clad wood.
Awesome. Thanks, Alice, for that question. Next up is Martin.
Hi there. Thanks for a great presentation. I was just curious in the layup of your IGU, if you had considered or run any tests on doing a laminate on the exterior most pane, and then spacer, and then tempered on the interior, thereby.
Yeah, no, probably help.
Okay.
A good question. So what I'm understanding from your question, and we thought of this, and there's some reason why not yet in the early testing. So your question is, why not have, out of the two lights at a minimum, make the inner one tempered, obviously, because to survive the heat, make the outer one laminated instead of tempered. So anneal glass and a plastic clear interlayer. And it would probably perform quite well. It would probably perform equally or better than just anneal glass on its own or tempered glass. The reason why we wanted to test without that is to see if we could get good results without that, because laminated glass is relatively costly. And if we could achieve passing results without needing that enhancement, then we're able to tell communities like everybody on this call, hey, these choices were enough in product configuration to get us to the point where we for sure pass this test. So you can do these things that are cheap, and you don't need to invest in laminated glass. But if you do want to invest in laminated glass, and you're doing it for other reasons too, like it enhances acoustics, it improves resistance to casual burglary a lot, then it will also, to some undefined extent, improve that unit's survivability in a wildfire. I'm not saying it's going to stay together, but it's going to stay together better than not laminated.
I mean, to that end, you could even go tempered and lami. I mean, from the production standpoint, it might be a little bit more challenging, but if you have the client willing to go there, it's kind of.
Yeah, I would, if a client asked me about that, I would look at what is their total glass makeup, because they might be asking for a triple glazed unit, they might be asking for a double glazed unit. If they're asking for a triple glazed, double or triple glazed unit, I wouldn't put the lami on the inside if the priority was wildfire resistance.
Sure, right.
But you typically would, if you're not concerned about wildfire, you typically would put the lami light on the inside, because it's the gentlest environment for the lami interlayer, and it has the longest potential service life because of that. So interesting trade-off there. Longevity of the unit might be minorly compromised by putting the lami on the outside, but it's better for wildfire resistance.
Right.
Good discussion. Thank you, Martin.
It's 10 o'clock.
So next up, we have Xenia.
Yeah, hi, Michael. It was a great presentation, and don't have a question, but a comment, because I'm working on a wildland in a wildland-urban interface area, and I think the recommendation is for the exterior pane to be tempered on a dual pane window. Do you know if that's correct?
Yeah, it's correct that there's some description in building regulations and the recipe like prescriptive version where they say temper the outer pane. My sense now, and actually I can speak as a group of the technical team at Underwriters Laboratory, technical team of engineers that did this research that Cascadia participated in, and our own opinion from seeing this. That's wrong from a scientific perspective. It is directionally correct when you think of like tempered glass improves resistance to breakage due to heat. Yes, but really, the outer light is going to break for sure. So it's basically a two-part equation. It's number one, how well will the broken outer light protect the inner light? And number two, how long will the inner light last? And so like that's really the variables in your equation, not can I get the outer light to survive? And so tempering the inner light will increase its survivability. If we look at the difference in annealed outer light, like not tempered outer light, to tempered outer light, like how long does it survive? So we tested both of those, and I'm bringing up this piece of our observations to just describe to you how quickly a non-tempered glass will break compared to tempered glass, because you can visualize if it's on the inside and the outside light breaks and goes away, how long will that inside light last on its own? So when it was the outside light, we observed that non-tempered glass will, if it's 1/4 inch thick, so relatively heavy, non-tempered glass will break between about 45 and 55 seconds into the 8 minutes. It will crack. Tempered glass lasts a lot longer, to the tune of 3 to 4 minutes. But it will break, and for sure always will break. But the inner light will only break, if it's directly exposed for those periods. So yeah, that there is. Thank you for bringing that up. There is some building code language out there that says temper the glass and make that the outer light. Like if you have to do that to comply with the code in that region, please also temper the inner light, because that's what's actually going to help.
Temper both.
Yeah.
Great.
So do the one for compliance before the code catches up, but do the inner one for true effectiveness, because that's what the science has now shown.
Yeah.
Yeah.
Thanks for that information. That's great.
Yeah. Thank you for bringing that up.
Thank you, Xenia. Next up, we have Brian.
Yeah, hi, thank you. Great presentation. I'm wondering if in your future studies you're looking at thermal radiant heat transfer through the glazing, because in urban configurations, especially where you have long-term intense heat really close to the windows, that heat can bring materials on the inside up to ignition point, so like drapes or couches or whatnot. And I know some people mention things like exterior shutters, but people aren't always home to close those, and automatic systems do fail. So, an extra protection for radiant heat. I was wondering what kind of studies or information you have on that.
Yeah, good question, and overall good point. So, number one, there is no silver bullet to like extinguish that risk, but there are steps you can do. We're not really doing more studies on it, which was kind of a part of how you phrased your question, but I do have some thoughts, which would basically be recommendations. Turns out that your low-E coating on your outer pane of glass actually is pretty good. It resists the amount of radiant heat that gets transferred to the inner light, and that's kind of helping the survivability of the inner light. If your outer light is annealed and mostly stays in place, like that's going to help during that moment. But in terms of just overall resistance to heat transfer, triple glazing is going to outperform double glazing, because like the outer light's going to break and then the fire is going to work on the middle light, and then eventually the middle light might break, and then the fire's gonna, but it's probably gonna be more, you know, unless it's catastrophic, the fire might be out by then before it starts to really impinge directly on the inner light. So that can help. So anybody who's selecting triple glazed windows for their thermal advantages in support of passive house guidelines, hey, you're also making a positive choice related to reducing the radiant heat transfer that you were bringing up, Brian. Exterior shutters, exterior mounted temporary coverings, yeah, all good. Temporary mounted coverings actually have a lot going for them, because it's not so much something you have to deal with architecturally, other than like a few little nondescript mounting points, but it is a user dependent thing. So the person has to be home when they're told to get ready to evacuate, and then they have to be, you know, willing to hang coverings when they're given the order to evacuate, or just before. They could hang them up a day in advance. So there's, yeah, like I said, there's no silver bullet there. Triple glazing is going to help. I didn't experience a really hardcore thermal transmission when I went and stood on the inboard side of the window while the fire was on. But once the tempered glass on the outside is broken and falls away, and the heat is on that inner light, like, yeah, you're not going to stand there for long. That's going to be warm. But it generally will, over the period of 8 minutes, it generally will keep all but the most flammable curtains from catching fire, because it's just 8 minutes, right? So anyway, yeah, thank you for bringing up that question and that topic.
Awesome, thank you. All right, William, you're up next.
Hey, I just had a simple thought about screens and wondered if they can be part of a strategy to kind of buy time in a fire, deflecting embers, or, you know, mitigating.
Yeah, good question. So they can either help slightly or hinder slightly if they're there, and actually there is no in between. So if you don't have a screen, then you're going to get the results you saw in our test photos. If you do have a screen, then you will either, if it's an aluminum screen, it will be moderately helpful or minorly helpful, in the sense that an ember that's coming through the air and might sit directly on your frame and cause earlier ignition than would otherwise occur from just a heat exposure, the screen will probably prevent that. And the screen won't burn. It will eventually melt and distort and fall off. Like it's going to be long gone before the halfway point of the test, but it's going to be there for a while, and it's not going to hurt the test. The opposite is unfortunately true if it's a non-aluminum screen, like if it's any other material. One of the most common material is glass strand with a PVC coating on it. That PVC coating will catch fire and burn, and it'll exacerbate the fire load. It'll make it worse for the window. The window will have to bear more. So if you have wildfire resistance in mind when you're speccing or purchasing windows, go for aluminum screen mesh. All the other factors are kind of just user choice, but go for aluminum screen mesh.
Great, thank you.
Awesome, thanks, William. John, you're up.
Are there any test results for metal-clad wood? And if not, are you considering doing some?
Good question. I don't have in my possession any photos or results from metal-clad wood. It might exist. If it does exist, it's probably an American manufactured product that has California as part of that manufacturer's market. I haven't done enough market research to know if there is a product that fits that mold, but I haven't been a party to testing with metal-clad wood. I will acknowledge that metal-clad wood would fit the list of recommended framing materials that FireSmart Canada published in their builder's checklist under the kind of the prescriptive guidance, when they said windows should be kind of this or this or this frame material. So what was absent from that list was exposed wood or PVC. So that was not on the recommended list. What was on the recommended list was like steel, metal-clad wood, thermally broken aluminum, fiberglass. For plans to test, Cascadia doesn't have any plans to test directly. partially because I don't think we have business buying another manufacturer's material and subjecting it to a test that they don't have control over. That's just, we could, but it doesn't seem to be good business ethics. It seems very aggressive, like we're trying to disprove something. So we would be present and supportive of a study that included manufacturers choosing freely to test their own material if they were metal-clad wood. We'd team up with them and we'd contribute product and time. But no, we're not going to go and try to play Mythbusters with some other manufacturers' products. Good question, though.
Thank you.
Yeah, thanks, John. Next is Mark Houston.
Hi. Question is pretty basic. How do the new thermal breaks on the aluminum windows react to the heat? And the other big question for me, I'm in Alaska, and we've got code issues with windows. Are you allowed to use LAMI in an egress window?
Okay, good question. I don't know what the melting temperature is of the polyamide thermal break in thermally broken aluminum windows. I'll tell you that it is definitely a lower temperature than would occur on the outside surface of the window during this fire test. So on the outside surface of the framing material, you're going to get temperatures ranging from like 900 to 1100 degrees Fahrenheit or more, depending on what points you're measuring. So for sure, the thermal breaks are going to suffer. They're going to melt. They might give up the frame depending on how holistically the frame is heated and really the sample size that is tested. But they will fare better than just exposed polymers like PVC or exposed wood. So yeah, they'll melt, they'll burn, but eventually. So during this 8-minute test, they'll probably fare much better as a metal cladding on the outside. So that's good for thermally broken aluminum windows. From a laminated glass perspective, you're actually asking a question that I don't know about. Egress requirements imposing limits on laminated glass. I do know that we as a supplier, where our target market does include Alaska, our products are directly available to customers throughout Alaska. We have never experienced a customer specification or technical support question on the permission to have LAMI glass in an egress window. That could be random circumstance. Maybe our customers never considered it, because an egress window is usually looking at a window that has to have its opening amount available to open to a certain extent and can't be restricted. But the glass itself is not usually part of that equation.
It usually has to be able to allow the firefighters to get through the glass. That's the other portion of it. That's my bigger concern.
That's a good point. Yeah, it needs to be breakable from a firefighter's perspective, and LAMI glass does not easily permit that. So
correct.
Yeah, in some locations on the building, if your building has that need, your building type, your building size, orientation, yeah, that would definitely be a concern where the firefighters need to be able to break in from the outside. So if that's a need for your building type, don't laminate the glass. If your acoustics rating,
and I would think, with the triple pane, it would definitely take longer. Obviously, if it weren't laminated, it would still last longer.
It would last longer in fire. Yeah.
Layers.
So this fire testing that we presented, we intentionally selected things where we wanted to test the sort of the worst case that would be economically viable and commonly procured. Like if, for example, if I presented this testing to you and said, well, we did it with triple glazing, your correct conclusion would be, well, if I'm trying to procure those windows with just double glazing, I can't count on those results being applicable. But you can the other way. Yeah.
Thank you.
Thank you for that.
Yeah, thank you, Mark. And we just got another question from Alice. So Alice, do you want to ask it?
Yes, thank you. When you're trying to make a passive house, and so you select glass specifically because you're in a cold winter area to let this heat from the sun in. I can't remember the number, what the words are. I know you all know it, but whatever that is for allowing lots of heat in, does that now make your windows way more dangerous for fire?
Good question. Fortunately, I believe the answer is no. You have not increased your risk of radiant heat transmission due to fire. A couple of reasons behind that. Number one, the presence or absence of a low E coating on the glass has only a minor, and in our limited testing, uncalculable effect. So it's going to, the existence of any low E coating compared to clear glass is going to be beneficial minorly, but so far there's not been enough testing looking at just checking that variable to see if it's quantifiable. So don't worry about that. Secondly, reason is that low E coating technology that allows incoming heat from the sun to pass through, but it still resists heat internally from being lost. That's selective because of the wavelength of that energy. So when heat is coming directly from the sun, it is at a higher frequency, and the low E coating technology is, and I'm going to use a sort of gross term here, just tuned to permit the passing through of that higher frequency heat directly from the sun. But once terrestrial objects like things on Earth are building, or some burning fuel outside is giving off heat, it's giving off heat at a longer wavelength, a lower frequency, and that will be reflected by a low E coating. So the heat from a fire would be, to some minor degree, reflected by any low E coating choice, just like heat from the interior that you're wanting to prevent losing is going to be reflected back into the building by any low E coating choice. Yeah, interesting question. Thank you.
Thank you so much.
Thanks, Alice. And Carolyn, you have a question.
Hi,
I don't know if you're
yes.
able. Yeah.
Thank you. Great presentation. When you were testing, did you test double and triple, or did you test both?
Good question. We just tested double. We knew that if we could get good results with double, that would basically be a given that you could expect that same result with triple. But we also knew that it would not be the same way in the other way around.
Excellent, excellent.
Good question.
And was they all fixed, or did you do some operable?
In this case, all these windows were fixed.
Okay.
We chose that, all the fiberglass ones. The vinyl ones that we bought off the shelf, they happen to be vertically single hung.
Okay.
Just because they were available that way. Cascadia will test fiberglass casement window and try to certify that. But at this point in time, for customers wanting the entire package of products to not only be wildfire resistant, which they could do by simply telling, like, if it's Cascadia order, just tell Cascadia, like, this is what I'm ordering. But we would also be compliant with the California requirements, kind of with a two-pronged strategy. Number one, all the products would be prescriptively compliant, utilizing tempered glazing and the glass package that's suitable for that. But also they would be built in the manner that passed the test.
All right, that's great. Thank you.
Yeah, thank you, Carolyn. Well, that brings us to the end of the questions, and this has been such a fantastic session, Michael. Thank you very much. I'm going to say a couple of words and then loop it back to you for any final words you want to share with us. A big thank you to Cascadia Windows and Doors for being a champion sponsor of Passive House Accelerator as well, and thank you, Chris Guelpa, who has been in the chat from Cascadia Windows. Thanks for being here and for helping to set this up. Really, really excellent. And I appreciate everyone's great comments and questions as well. This discussion has been as good as the excellent presentation. So thanks for everyone's contributions to make that happen as well. If you're interested in diving more into materials and components and the Wildland-Urban Interface, in November, we have the component spotlight that I think that Kim mentioned in chat earlier with Rockwell. And I think that she's going to, there's the upcoming event with Rockwell. So please join us for that. And of course, next week at Passive House Accelerator, Accelerator Live on Wednesday. We're joined by the folks from Passive House, Massachusetts, and the Massachusetts Clean Energy Center to dive into the really exciting work that's happening in Massachusetts around Passive House. So we'd love to see you for that. We're just looking forward to seeing you next time. So with that, Michael, any final words for all of us?
Great. Yeah, thank you for everyone sticking on the call past the top of the hour and for inviting Cascadia to share with you. Our work with this subject of wildfire resistance and the related testing is ongoing. So like I said at the beginning, happy to have shared what we have done so far. If you're looking for more follow-up from us, of course, this organization is great for that, but also directly Cascadia will, as knowledge is accumulated, share that most commonly through the form of webinars. So our webinar on this topic will update so like next year as more is learned.
Awesome. Great. Thank you. Thanks, everyone. Happy Thursday. We'll see you next time.